Welcome to Calc 3. This is the second part of section 13.6, triple integrals with examples. Let's first off start out with this problem, the triple integral from 0 to 1, 0 to pi, 0 to z, of sine of yx with respect to x, with respect to z, with respect to y. So first off, we notice that x here is not represented in the integrand. So x, we can say this is actually a separable function. So we can say 0 to 1, 0 to pi, sine of yz times, and we can actually separate out the integral from 0 to z of dx. We can put a placeholder with a 1 here, dx, dz, dy. And so what this does is we can't bring this integrand outside of the dz because it has a z involved in it, but we can evaluate this. And so we get 0 to 1, 0 to pi, z sine of yz, dz, dy. And so when we look at this function now, with respect to z, this looks like quite the tricky integral. So it's a good time to consider changing our bounds, because with respect to z, a u substitution isn't necessarily going to work here because we've got a z on the inside of the sine function and the outside of a sine function. So a u substitution on the inside would leave us with a y as our coefficient, which doesn't help. Integration by parts might work, but there might be an easier way since we're allowed to switch our bounds. So let's look at our bounds for constant bounds. So here, y has bounds 0 to 1, z has bounds 0 to pi. So if we consider what this function looks like, this region looks like on the yz bounds, we're looking at a square. So using Fubini's theorem, instead of integrating with respect to z first, we can change the order integration and integrate with respect to y first. And so if we change our order of integration, changing the order of the rectangle orientation, we keep our same inside, and we swap our bounds, making sure to preserve our region, which it's a rectangle, so just swapping the order of the bounds preserves our region. Now when we do a u substitution, u equals yz, then du is equal to what is equal to z dy, because we're integrating with respect to y. So 1 over z du equals dy. So this inside piece becomes sine of u du, which is much easier to integrate. So then we get the integral 0 to 1, or excuse me, 0 to pi of negative cosine of yz evaluated from 0 to 1 of dz, or times dz. So we get 0 to pi of negative cosine of z, and then cosine of 0 is 1, so we get plus 1 dz. So this gives us negative sine of z plus z evaluated from 0 to pi. Sine at pi is negative 1, so we get positive 1 plus pi. Sine at 0, or excuse me, sine at pi is 0, so we get 0 plus pi, and then sine at 0 is 0 plus 0, so we get equals pi. So our second example, let's look at this lovely function. So we have the triple integral from pi to pi squared, from x to x cubed, from negative y squared to y squared, of z times this integral, or this function, x squared times y plus y squared times x over e to the x squared plus y squared, dz, dy, dx. And so as with many problems, just take it one step at a time. So let's look at the innermost function. So our innermost function, we say the only thing with respect to z is z squared times some stuff. So we get 1/2 z squared times our coefficient. I'm going to indicate with a dot here. So this piece just all carries down because it has no constants in it, or no z's in it rather. It's completely a constant. So negative y squared to y squared. And this is z equals negative y squared to y squared. So this becomes 1/2 y to the 4th times the stuff minus 1/2 y to the 4th times the same stuff. And so we have positive 1/2 y to the 4th times stuff minus 1/2 y to the 4th times stuff equals 0. So then when we're doing our integral, pi squared, or pi to pi squared, x to x cubed times 0 dy dx, this will be 0. Because no matter what I do, I'm going to get pi to pi squared times some constant x to x cubed dx. But a constant, there's no values, there's no y values to drop in my x to x cubed, so I'm still going to get 0. So pi to pi squared of 0 dx. So I'm always going to get 0 out. And so with respect to z, why does this make sense? Well, if we consider what the function looks like on the y-z axis, so z equals y squared looks like this. Z equals negative y squared looks like this. And if I'm looking for the area between this, remember from Calc 1 that integrals look at the area between the two curves, and if the areas cancel each other out, then the area is equal to 0. So here the areas cancel, and that's why our area is equal to 0. So it turns out that we have enough area on the top to balance the area on the bottom. So we essentially have no volume, even though we had an interesting function, we have no volume over this region. So as always, if you have questions, please let me know.